Okay, we're going to be talking about the domain when given an equation, an algebraic equation and not a graph. Unless specified otherwise, the domain is assumed to be all real numbers when substituted for the independent variable. So in general, the domain of a function is all real numbers except for those that lead to division by zero or an even root of a negative number. So if it's not division by zero or an even root of a negative number, then we assume it to be all real numbers. So let's look at number 5, and we're just going to be doing the domain of these. Decide whether each relation is a function and give the domain. We say yes, this is a function. And we can see that because y is always found by adding 6 to x. Thus, each x value will have exactly one y value to go with it. So this is a function. Okay? And it's not led by division by zero, and it doesn't have a radical, so the domain is going to be negative infinity to positive infinity. Okay, we move up and we look at B. For any choice of x in the domain of the square of this function, in the domain of this, there's exactly one corresponding value for y. So anytime you substitute a value in for x in calculator, you're going to get one value for y. Okay? Since this is a radical, we know that the square root portion, the radicand, we call this the radicand, has to be greater than or equal to 0 because it cannot be a negative number. And all greater than or equal to 0 does on a number line, greater than or equal to 0, so it means when it says greater than or equal to 0, it ensures that it's positive. So that's why we picked this. And all we're saying is that this radicand has to be positive, and that's all we're doing. So we solve this, and we would get 2x is greater than or equal to 4. Divide both sides by 2, and x must be greater than or equal to 2 for us to get a positive number under here. So to name that, if I drew that on a number line, that would be a bracket because of that bar, greater than 2. So if I was to name this, the domain is bracket 2 to infinity. Okay, so that's our domain. Let's look at C. First of all, C is not going to be a function, and let me just pick an ordered pair to show you why. So for example, if I had the ordered pair 16, 4, and I had the ordered pair 16, negative 4, we can see that the x value of 16 is paired to two different y values, which means not a function. Okay? And I just picked those points and calculated them because if you pick 16 right there, 4 squared, if you put a 4 for y, 4 squared equals 16. But if you put negative 4 right there, 4 squared equals 16, and negative 4 squared equals 16. So that's why we can see that this fails to be a function. Alright, so since when we're talking about the domain, since x is equal to the square of y, it's always positive because any number squared is always going to be a positive number. So all that tells us is that the domain is always going to be positive. And we kind of talked about always positive up here, and that means greater than 0. Anything bigger than 0 is going to guarantee us to be positive. And once again, we said it has to be positive because anything squared will give us a positive number. 4 squared gives us a positive number. Negative 4 squared will give us a positive number. So the domain is all the positive numbers. And we look at D. We said D is a function because given any value of x that's in the domain of this thing, we find y by subtracting 2 from x and then dividing the result into 3. Thus, one value of y for each value in the domain of x. But this, we could have division by zero. So let me scroll back up. If you lead to division by zero, so anytime we have a fraction, we take the denominator and set it not equal to zero. And we say x cannot equal 2. The reason why x cannot equal 2 is because if I put a 2 right there, 2 minus 2 is 0, and that's an undefined function. We would get 0 on the bottom when we can't have that. So it means x can be anything but 2. So if I drew a number line, it means at 2 it can't equal 2, but it can equal everything over here, and it can equal everything over here. So the domain would be negative infinity to 2 union 2 to positive infinity. So that's going to be your domain. Function notation basically just says y is a function of x. And this emphasizes that y depends on x. So we use this function notation and we read this as f of x. F of 2 is the y value that corresponds to the x value of 2. Let's see this in action to help you understand this a little better. Okay, this says go to the f function and write it down. So I'll go to my f function and it's right here. So I would say f of x is equal to negative x squared minus 5x plus 2. F of 2 says everywhere there's an x, put a parenthesis, and then go back and fill it in with the 2. And then we calculate. 2 squared is 4. Bring down that negative. Negative 5 times 2 is negative 10. Plus 2 would be negative 14 plus 2 is negative 12. So I would say f of negative 2 is equal to negative 12. Okay, so let's evaluate f at m. Okay, so that means go to the f function, write it down. F is, go to the f function, negative x squared minus 5x plus 2. Everywhere there's an x, put a parenthesis. And then this says substitute m everywhere you see an x. So put m. So this is going to be f of m. Okay, this next one says go to the g function and write it down. So I have 4x plus 1, and I'm getting that from my g of x is 4x plus 1. Everywhere there's an x, put a parenthesis, and we're going to substitute 4 in place of that. So I would get 4 times 4 is 16, plus 1 is 17. So I would say g of 4 is equal to 17. And then my last one says go to the g function, write it down. 4x plus 1. Everywhere there's an x, put a parenthesis. Okay, this says substitute p plus 1 everywhere you have an x. And then we just distribute and simplify. 4p plus 4 plus 1 is equal to 4p plus 5. So g of p plus 1 is equal to 4p plus 5. For each function, find f of 2. So that means everywhere there's an x, substitute a 2 in place of it. 2 times 2 is 4. 4 minus 4 is 0. Okay, if I'm looking for f at 2, I'm looking for when the x value is 2, what is the y value? And so f at 2 for this is 5. For part C, f at 2 is 3. Okay, for this particular one, D, I'm actually going to look at f at 5. So basically what you're going to do is you go to the x value of 5, which is right here. You go down to meet your graph, your function, and then arrow over to see what the y value is. Negative 4. So if I was to do f at -1, what I would do is I'd start here, go to the x value of -1, go down to my graph, and then arrow over to see what the y value would be. So let me draw it with my pen. I would go to -1, arrow down to my graph, and then back over to my y-axis to see that would be -2. Writing equations in function notation. First of all, assume y is a function of x, rewrite in function notation, and then find this and find this. So function notation just says replace y with f of x, and it'll be exactly the same. Okay, and then the next one says evaluate f at -3, which means everywhere there's an x, plug in -3. So that would be -3 squared is 9, plus -3 minus 2 is going to be 4. F at b says everywhere there's an x, plug in a b. So that would be b squared plus b minus 2. Everywhere there's an x, plug in a b. Alright, we do the same thing for b, except for to write this thing in function notation, we have to solve for y equals. So let's move 6x to the other side. I would have -2y equals -6x plus 8. Divide both sides by -2. Y equals 3x minus 4. So function notation we replace with f of x. That's all we do for function notation. For f of -3, we replace x with -3. And then that would give us -9 minus 4, which is -13. And then the last one says f of b, meaning everywhere there's an x, put a b. Okay, and so that's it on functions.